All right, so for question 1, we have for our octagonal chart, I used the visual references down here and found that overlapping, we would always have dots from each of our octagons that would be repeated. And so for 1, it was this one in the corner. For level 2, at level 3, it would be this one, and then these 3. And then at level 4, it would be all of these here. And so for level 2, I found for octagonal to be 8. For level 3, I found it to be 21. And at level 4, I found it to be 40. We would just use the overlapped plus however many dots was left. But we would not, we would not count those more than once. So we would only count them one time. And so I did the same thing with decagonal over here. And so here you see we have 8, 21, 40, 65, and so on, and then 10, 27, 52, 85, and so on. And for our n for octagonal, I found it to be 3n squared minus 2n, and for decagonal, I found it to be 4n squared plus 3n. Finding a pattern to generalize for each of our levels for any p-gonal shape. I found that for level 2, it would be p. For level 3, it would be 3p minus 3. If you just look at the relationship between all of the numbers in our chart, we find that 3 times 6 minus 3 gives us 15. 3 times 8 minus 3 gives us 21. And then 3 times 10 minus 3 gives us 27. And so I found that relationship for each level and generalized it. So for level 4, we have 6p minus 8, 5 is 10p minus 15, 6 is 15p minus 24, and so on. And then to generalize even more to find any number n, I found that the quantity p minus 2 over 2 times n squared minus n times the quantity p over 2 minus 2 would give us a number of dots for any n of any p-gonal shape. For number 2, I found the distance for Euclidean to be 5.65, and that was just using the Pythagorean theorem. I then divided that by 2 to get a midpoint of 2.83, and I drew Euclidean circles with a radius that was a little bigger to find a spot where they would overlap for the park to be. I then drew in our perpendicular bisector, and on this line the park could be placed anywhere, and it would be equidistant from both Poly-Eyes and the gas station. For taxicab geometry, I did sort of the same thing, so I found the distance to be 8 because we have R4 plus R4, and then I divided by 2 to get a midpoint of 4. So I drew 2 Euclidean circles, which look like squares, around both Poly-Eyes and the gas station. And I found our overlapping points in our perpendicular bisector. And all of these points here are included. And so the part can be placed anywhere on these lines, and it would be equidistant from both Poly-Eyes and the gas station. If we look at the next part of this question, if we have an odd distance, there won't be a point that's equidistant for the part to be placed. And so any point that gives you an odd distance is what you could have plotted so that the park would not exist in taxicab geometry. This is because having an odd distance gives us a half of a block, and we can't have a half of a block in taxicab geometry. So here you see I did 7 and 4. For question number 3, I found that the distance was 19.235. I did 9 squared plus 17 squared, and I took the square root to get our hypotenuse. For B, I found the distance along the edge to be 26 miles, and that was the distance using taxicab. And for C, I used what we found with the relationship between Pascal's triangle, and how up here you can only get there one direction, and down here you can only get there one direction. And then finding how many ways you can get to each point starting from this corner. And I found a total number of 2,011,943 different paths that you could take by using this formula here. So I just found that this distance